First of all, looking back at the homework, what's the difference between climate and weather? The short version with that is that climate is the long-term average of weather conditions. Weather is the instantaneous conditions in the atmosphere at any one time or any one place, and climate is the long-term average of all those conditions. So we look at a climate as the average condition over numerous years, whereas the weather is the conditions over the course of maybe a few hours, a few minutes, or perhaps a day or so. So for this, it's really all about the length of time. What two gases make up most of the atmosphere? Nitrogen, oxygen. Which one is more prevalent? Nitrogen. Way more nitrogen than anything else. What's the term trace gases mean? Trace gas means it's a gas that there's very tiny bits of in the overall atmosphere, very minuscule parts in the atmosphere. Are any of those important? Yeah. If so, why? Carbon dioxide, water vapor, ozone. Tiny, tiny amounts of those gases in the atmosphere compared to oxygen and nitrogen. All right, but because they're very active in the infrared part of the spectrum, they do a lot regarding absorption of certain wavelengths of electromagnetic radiation. Carbon dioxide, water vapor, very, very active in the infrared part of the spectrum. That's why those are the two greenhouse gases that we're most concerned about. Ozone absorbs ultraviolet. So, and again, there's less ozone than there is water vapor. There's less ozone than there is carbon dioxide, but it still absorbs the vast majority of ultraviolet radiation that's coming from the suns, so we don't get sunburned every time we go outside. Difference between climate change and climate variability. Climate variability is the fluctuation around a mean state. It's the normal fluctuations in a climate. All right, you're not heading into a fundamentally different climate regime. Climate change means you're going in a certain direction. You might have little ups and downs on the way, but you're definitely on a one-way warming track or a one-way cooling track. That is a climate change. You're going to a climate that is much wetter, one that is much drier, all right, as opposed to these internal variabilities here and there. So that's the difference between the two. Variability is changes around the mean state. Climate change is a big change in one specific direction. In situ measurements and remote sensing. An in situ measurement means you're inside of the medium that you are measuring. All right, when you have a thermometer, a liquid and glass thermometer, if you put it in a pot of water, you're actually in the water that you're measuring the temperature of. Same thing with just thermometer in the air. Remote sensing means you're not in the medium in which you're trying to measure. So remote sensing is generally by satellite, sometimes by radar, which we'll talk about a little bit later in the lecture tonight. But remote sense means you're remote from the object you're trying to get information about. If I'm in orbit and I'm trying to get information about the Earth's biosphere, I'm getting it remotely, either by sending a pulse of electromagnetic radiation down and watching it bounce back up, or just standing up there in orbit, waiting for the energy to come up at me. So that's remote sensing, as opposed to being down on the ground, measuring the chlorophyll in a leaf directly. So that's the difference between those two things. How much does the amount of energy coming from a surface increase as the temperature increases? This is sigma T to the fourth. All right. The important thing here is that you remember that the amount of energy goes as the fourth power of the temperature. It's not linear. The amount of energy goes up at 4 times, or not 4 times, excuse me, to the fourth power of temperature, and that's in kelvins. The electromagnetic spectrum from lowest energy to highest energy. What I actually did here is I flipped it, but you get the idea. Highest energy here is gamma rays, then X-rays, then ultraviolet, then visible, and then infrared, microwaves, and radio waves. So I flipped the numbers here. But the idea is that gamma rays are the most intense, down to radio waves being the least intense. Why does the sun not rise to the South Pole for several weeks around the end of June? Remember that the Earth is round, the South Pole is at the bottom. Remember that the Earth is not straight up and down on its axis, it's tilted at an angle of about 23.5 degrees. So by the time we get to June, which is northern hemisphere summer, we are tilted toward the sun, getting direct rays from the sun, but the South Pole is not getting any direct rays from the sun at all. That means that the sun is not coming up until the Earth goes around far enough by July, where the sun begins to rise there, because the sun, Earth in its orbit around the sun finally starts to pick up a few rays of sunlight. So that's the short version of the homework. And I'll have those grades up later on this week. Oh, one last thing, why might a fresh snow have higher albedo than one that's been on the ground for several days? Albedo is reflectivity. So a brand new fresh snow is very white and very reflective. After 4 or 5 days, you've got people driving around, you've got animals running around on it. So you're getting imperfect, you're getting impurities into the snow. You're getting dirtier snow because it's been out there for 3 or 4 days. So it's not as fresh, it's not as reflective. So that new snow has a higher albedo, it has a higher reflectivity than snow that's been around 4, 5, 6 days. All right, shorter version of the lecture tonight. Again, the primary lecture notes have already been uploaded to Moodle, but the 3 main points here from this particular lecture: water in the Earth's climate system, different ways to describe water in the atmosphere, how air becomes saturated to form clouds, and then the formation and types of precipitation. So we start with the global water cycle. It will probably not surprise anybody that the ocean is the largest reservoir of water on Earth, accounting for about 97% of all water on Earth. After that, most of it is locked up in ice, generally glacial ice, either in Antarctica or Greenland. That's where most of the rest of the water is. The global water cycle, sometimes you hear this as the hydrological cycle, but it's this movement of water between the atmosphere, ocean, biosphere, terrestrial spheres, all on the planetary scale. So this is the schematic of that, the classic 3-prong thing that you may remember from grade school: evaporation, condensation, and precipitation. Water evaporates, goes into the sky, it cools, and so it condenses. That's the condensation that forms clouds. And basically, once you get enough of that, you start to become heavy enough where your water droplets or ice crystals begin to fall to the ground, and that's precipitation. So that's the big 3. Transpiration, that is a process where plants are taking water out of the soil through the roots, sending it out through the leaves. It's going through photosynthesis, releasing water back into the atmosphere. Humidity is more than just a percentage. What do we mean by that? Humidity is a generic term for water in the air, water vapor in the atmosphere. When we say humidity, that's all it means. It's water vapor in the atmosphere. And it varies a lot from season to season, from one day to next, within a day, from one place to another. It's certainly not consistent throughout the entire Earth system. One of the things you'll probably see on your weather app the most is the relative humidity. The relative humidity, what does the relative mean? It means relative to temperature, right? Because as the temperature goes up, the capacity of air to evaporate water goes up because it's higher energy. So if your air is warmer, that's more energy. So that means there's a higher capability to evaporate water from a surface into the air, into the atmosphere. All right, you put a glass of water in a room that's 80 degrees, you put same glass of water in a room that's 50 degrees, you're going to have a lot more evaporation in that room that's 80 degrees. All right, and conversely, you will probably reach a saturation point much more quickly in the air in a room with a lower temperature. So expressed as a percentage, when the air is saturated, no matter what that temperature is, if it is saturated, that value is at 100%. Right? It may not feel humid, like if it's pouring down rain outside and 36 degrees, the relative humidity is 100%, but it might not necessarily feel humid to you outside. The flip side of that, during the summer, it might be 95 degrees out, but the humidity, relative humidity, is 45%. The relative humidity is small, but it still feels awfully, awfully muggy outside. There is a lot more water vapor actually in the atmosphere per unit volume of air, but that's what your body is responding to, the individual water vapor molecules, all right, not necessarily the relative humidity in and of itself. What you will hear meteorologists, climatologists use much more frequently is something called the dew point temperature. All right, that's the temperature at which the air must be cooled at a constant pressure to saturate. All right, so the higher the dew point temperature, that means the higher amount of moisture that's physically present in the air, regardless of what the temperature is. So we say that's an absolute humidity. The dew point temperature is a measure of absolute humidity. All right, there is a correlation between the dew point temperature, not the actual air temperature, the dew point temperature, and how many water molecules are running around per unit volume of atmosphere. All right, so the higher the dew point temperature, or just dew point for short, the greater the concentration of water vapor in the air. So I said before, it could be pouring down rain 38 degrees. That means the atmosphere is saturated. So the dew point temperature is also 38 degrees. Dew point temperature and the actual temperature are the same. The relative humidity is 100%. All right. Conversely, in the middle of summer, it's 95 degrees outside. The relative humidity is 45%, which sounds low. All right. But the dew point temperature is 70. All right. So that's still a big, big spread between the air temperature 95, dew point temperature is 70. That means the air would have to cool to 70 degrees before you would start to form clouds, fog, condensation. Right? That is powerfully humid. All right? That is muggy by all sense of the imagination. All right? We don't really see the dew point temperature on Earth very much go past about 80 or 85 in very tropical latitudes because it takes an awful lot of energy to evaporate that much moisture. And the capacity to hold moisture in the atmosphere goes up dramatically with temperature. It's nonlinear, right? It goes up dramatically as the temperature rises. Dew itself basically forms when water vapor condenses onto something, whether it's the side of the glass or whether it's grass first thing in the morning. Basically, you've got water vapor that's coming into contact with the cold surface, and it condenses right on that surface. That's dew. It's not really precipitation. So how do we make clouds? The condensation, or sometimes deposition. Remember, deposition is when you go straight from a water vapor, you skip the liquid stage and you go right to a solid. That's deposition. And that becomes more and more likely, obviously, as the relative humidity gets close to 100%. And that's when you start to get clouds getting up into the sky. Clouds are a visible aggregate of water droplets and or ice crystals in the atmosphere. Right? There is water vapor mixed in there too, but water vapor is invisible. You can't see water vapor. Clouds are solid and liquid, solid and or liquid. There's water vapor mixed in there as well, but you can't see the water vapor. Clouds are liquid water droplets and or ice crystals. So how does the air become saturated? All right, there's a couple of ways to do this. One, you just cool it. You cool the air, and if you don't change the number of water vapor molecules in that same volume of air, and you just cool it, you get to that dew point temperature, and suddenly you got a little chunk of saturated air, and you got dew or clouds forming. All right. So what are some ways to do that? Expansional cooling. A gas or mixture expands, the temperature decreases. This is the classic air rises, it cools and forms clouds. Well, as the air rises, it cools because it's expanding. It's going from an area of high pressure here close to the ground, all right, at 14 pounds per square inch. It starts to rise higher in the atmosphere, all right? Now you've got less air over top of you because maybe you've gone up 2, 3, 4,000 feet. So the weight of the air over that point, 3,000, 4,000 feet up, all right, is a lot less than the weight of the air down here at the surface or at the ground level. All right. So the pressure down here at the ground is higher than the pressure 3, 4, 5,000 feet up. So as that air rises, it expands and cools. So that's expansional cooling. And the reverse is true, compressional warming. You take air 4, 5, 6,000 feet up and you start bringing that down in whatever way you decide to do it. All right. Either most of the time you've got air coming down a mountain. You have air going up and then coming back down a mountain. That's how it happens most of the time. It's being compressed. It goes to an area of relatively lower atmospheric pressure, 9, 10,000 feet, if you will, all the way down here to sea level. That air comes down, it gets compressed or squeezed, and it warms up. And when it warms up, that means if you had a saturated piece of air up here, 5,000, 6,000 feet, and it gets compressed and warmed, you're moving away from saturation because your air has warmed. You haven't changed the amount of water vapor, but you've warmed the air, all right? And so no longer at saturation.
So is that like why, like with expansional cooling, is that why like it's always snowing like on the western slopes of West Virginia?
Bingo. That's
right.
Exactly it. That air, you've got air that's almost saturated, runs up the western side of the Appalachians. It's cooled, it's expanding, you form clouds, and then it starts to precipitate out snow. And then as it starts to come, does that same air begins to come down the other side? It warms up, it stops snowing, and the clouds break apart, and actually the sun comes out 60, 70, 80 miles downstream, or downwind, not stream, but downwind of that. So that's exactly why you've got a place like Pittsburgh, like Charleston, West Virginia, Erie, Pennsylvania. Those places have awfully cloudy winters. For that reason, they're on the western side of the peak of the Appalachians because the prevailing wind direction in the winter is from the west or northwest. I mean, it shifts sometimes, but the prevailing, or the average wind direction through the winter is from the west and northwest. That same air then comes down the eastern side of the Appalachians and gets to New York or Philly or DC or Richmond or Raleigh. And it's come down those mountains, it has warmed up. So the clouds dissipate, sun comes up, sun comes out. And you see that all the time during the winter. I was shocked at how often it happened until I went to college. And I was like, holy, I cannot believe how cloudy it is. Because I grew up in Richmond. I go to the central mountains of Pennsylvania to go to college, and I just pull all what's left of my hair out because it's so cloudy during the winter, just for that reason. All right. Now, this expansional cooling, compressional warming of unsaturated air are called adiabatic processes. Sometimes we call them a diabatic process. A diabatic process, diabatic process is a process that adds or removes heat from a system. All right. So if you have an adiabatic process, you're not adding heat or taking heat away from the system. All right. So as it says here, as an air parcel, a little chunk of air goes up or down through the atmosphere, it's not exchanging any heat with the surrounding air. All right. And this is how we're able to make some kind of determination of what temperatures are going to be as they go up and down through the atmosphere. And we're saying unsaturated because once you start playing with saturated air, you've got latent heat involved again. That change of phase between liquid to solid, liquid to gas, those kinds of things. So then you are exchanging heat. Right? But if you're not playing with saturated air, your air is unsaturated. That's the adiabatic process. All right. So what is the rate of that? All right, the dry adiabatic lapse rate. All right. So this says for every 1,000 meters, it's a kilometer. It's 0.6 miles. Okay, 3,000 feet. You change the temperature about 10 degrees Celsius. All right. So if you have a chunk of air that's dry, not much water vapor in it, and it starts out 50 degrees Celsius, 50 degrees Fahrenheit, 10 degrees Celsius. Then you take it up about 1,000 meters, 3,000-ish feet, and the temperature drops about 10 degrees C. So it goes from 10 C to 0 C in that 1,000 meters going up. So it's 50 Fahrenheit, 32 Fahrenheit. You're dropping 18 degrees in about 3,000 feet. All else being equal. All right. Now, once you do have saturation involved, we call that the moist adiabatic lapse rate, because the thing hits saturation and you're not going to cool things as rapidly anymore, because it's not a true adiabatic process anymore, because there is still some heat released. It's still called the moist adiabatic lapse rate, but there's no external heat being brought in or removed from the system. It is still within that little chunk of air, if you will, going up. All right. So when that's the case, that lapse rate is 6 degrees C instead of close to 10. Right? Because it's still cooling as you go up. But once you start releasing energy as latent heat, remember, you go from a vapor to a liquid, that's going to be releasing heat into the atmosphere. Right? So as a result, your cooling rate will not be as fast because of that. Stability in the atmosphere is very important when we start thinking about wintertime precipitation, which we'll get into in a minute. Atmospheric stability tells us what the temperature profile of the atmosphere is vertically. All right. We compare the temperature of a little chunk of air going up or going down with the temperature of the ambient air around it. All right. So for example, let's take that little piece of air. It's down here on the ground. It's 50 degrees Fahrenheit. If the air that's kind of blowing in from a different direction, 1,000 feet up, is 35 degrees Fahrenheit, all right, and this air starts to rise, all right, it is cooling, but if the air around it is still colder, then it's going to continue to rise, because I've taken a little piece of air that's up, but it's still colder than the air that surrounds it. So it's positively buoyant, so it's going to go up further. All right. The reverse is true. We see this a lot in winter when it comes to non-snow precipitation. That's ice. What I mean by that is sleet, freezing rain. All right. So you might have air down here at the ground that's 28 degrees Fahrenheit, but the air maybe 3,000 feet up is 42 degrees Fahrenheit. So the air is actually warmer a few thousand feet higher. That's very stable. If you were to try to take some of that 28-degree air up into the atmosphere, it's still way, way colder than the air that's above it. So it's going to have a tendency to sink back down. So we say that's very stable. All right. Sometimes, and we see this a lot in the spring and early summer, the air 5, 10, 15, 20,000 feet up is still very, very cold from the winter. So the sun comes up and the sun's getting higher in the sky by April and May. That heats the ground. Ground heats the air over top of it. That air starts to rise, and just very, very cold air that's over top of that. So it races up like a hot air balloon, forms clouds, precipitation, and thunderstorms. That's why thunderstorms are most common in the spring and early summer, because the atmosphere 5, 10, 15, 20,000 feet in the sky is still very, very cold. It takes a long, long time for the upper part of the atmosphere to warm up for the summer, much like the ocean does. It takes a long, long time for air in the upper part of the atmosphere and the ocean to finally come into balance with the incoming solar energy through the season. So when we talk about the two classical ways that precipitation is formed in the atmosphere, when we talk about fronts, warm fronts, cold fronts, that kind of stuff, a cold front is just an area where you've got that cold air advancing and warm air retreating, and that's the boundary between those two things. And it's the same thing for a warm front. Warm front, warm air is advancing, cold air is retreating. cold front's advancing, warm air is retreating. All right. As the warm air advances, that top frame, the warm air runs into that colder air. Cold air is more dense than warm air. All right. So the cold air doesn't retreat as fast as this warm air. So basically, warm air bumps into the cold air and starts gliding over top of it. So you start to get a gradual formation of clouds and ultimately rainfall. But you don't have torrential, crazy, heavy downpours most of the time with this overrunning of warm air over cold air. Now, when the cold air advances, like we really see during the winter, because it is shallow, it is more dense. As it comes in, it smashes into the warm air, forces the warm air up much more rapidly. So this is where you're getting thunderstorms. This warm air goes up very rapidly into some much colder air over top of it, and then you start to have this billowing thunderstorms. We call convective precipitation. This tends to be shorter lived but heavier than what's nicknamed stratiform precipitation there in the top diagram. So which clouds are which? There's all kinds of cloud types, but we'll get into the specific classifications. It's important to know the basic ones. You don't need to know 40 different cloud types because it's just not that important. All right. But to get clouds to form in the first place, you need to have some impurities in the atmosphere, some impurities in the air. So water vapor doesn't just up and form liquid when it cools to 32 degrees Fahrenheit. All right. And liquid water doesn't just automatically freeze once it gets below 0 degrees Celsius. All right. So if you've got liquid that's 40, 39, 38, 37, 32 Fahrenheit, once it hits 32 Fahrenheit, it doesn't just magically freeze. All right. You need some impurity for that ice crystal to build itself on. I've got a little liquid water drop, 33 degrees, hits 32. Yes, I'm going to start giving up some latent heat so I could drop it to a lower energy state and form an ice crystal. But I need something for that ice crystal to form on. And that's called a cloud condensation nuclei, or CCN. All right. So even a teeny microscopic piece of dust, that's all you need to get the thing started. Ice forming nuclei is the same thing. Something to nucleate on, something so when you drop from a higher energy phase to the next lower energy phase, your molecules can start to organize around something. Very, very tiny, but around something. Now, to be fair, you can have, and I love this, you can have liquid water droplets well below zero. It gets harder and harder until you get down to, and I love this, minus 40. Minus 40 Fahrenheit is actually the same as minus 40 Celsius. Once you get to minus 40, you get what's called, I love this term, spontaneous nucleation. That's when liquid water will start to use its own molecules to form ice crystals around. That's kind of wild. The weird things you remember from school. But again, that's at minus 40. Point being is you can have liquid water that's below the freezing point. That's called supercooled water because you've got liquid water that's below the classical freezing point of 32 degrees Fahrenheit. So these are the primary cloud types. Cirrus cloud, high clouds start with that CIRR prefix. All right. Cirrus clouds are any clouds that are high clouds, 5,000 meters or higher. All right, so 5 kilometers, 3 miles. Clouds are generally 3 miles or higher, 15,000 feet. They're up there a good ways. So they tend to be kind of wispy. So cirrostratus, stratus is a term that means flat, it means layered, it means stable. So cirrostratus clouds are high clouds that are just kind of flat, right? Cumulus tends to mean bumpy. So we don't see a lot of cirrocumulus, but these are high clouds that look kind of bumpy, kind of like a mackerel appearance in the sky. I mean, they're way up there, 15, 20,000 feet, but sometimes look like teeny tiny cotton balls very high up in the sky. So cirrocumulus. But CIRR, that's the prefix you need to remember for clouds that are high clouds. Middle clouds between about 2,000 and 5,000 meters, so 2 to 5 kilometers. So you're taking a shade over a mile to about 3 miles up. All right. Alto. Alto is the prefix for middle. And the same thing. Alto stratus, those are mid-level clouds that are kind of flat. Alto cumulus or mid-level clouds are a little bit bumpy. And then you got the bottom one, stratus clouds. Stratus clouds are just gray, low to the ground, less than 2,000 feet. Stratocumulus are kind of flat, but they have little bumps in them. And you see those a lot during the summer and during the dead of winter. Nimbostratus are clouds where you can't even see that they're clouds. You're not really in fog, but if you're in a rainstorm or in a snowstorm, the clouds that are producing those are nimbostratus clouds. All right, they're very low to the ground. They're the ones that are ultimately producing the low level, or the ones in place close to the ground. I mean, the precipitation is being produced higher up, but it's passing through these lower levels of the atmosphere. You've got saturation. You've got this grayness hanging all over you from horizon to horizon. Those are the nimbostratus clouds. Clouds with vertical developments, that's that cumulus. Any kind of cumulus is this billowing, bumpy, cauliflower type thing. And the cumulonimbus, that's the thunderhead cloud. That's the technical name of the thunderhead cloud. These are the things that are going up 20, 25,000 feet from the ground up easily, 25, 30, 35,000 feet into the sky. So they have vertical development. High clouds are just, the cloud base is up here 3-4 miles up. For the cumulonimbus, the cloud base is still close to the ground, but the cloud goes from the ground 15, 20, 25,000 feet up or higher. All right, so you've got clouds with vertical development. They're not necessarily spread out one direction. These vertical development is what we call cumulonimbus clouds. All right, a little bit about precipitation. Two methods to form precipitation. Once you start getting saturation or deposition, you've got liquid and you've got ice in a cloud. All right, so when we say warm is shorthand for above freezing. All right, so when you have liquid water droplets, and it's almost, and this is mostly the summertime, and in areas below about 15,000 feet, when your cloud is almost all liquid water drops, they start very, very tiny. They're microscopic water droplets. They're tiny, but they're liquid. They start to coalesce, bump, collide, get a little bigger, and that keeps going and going and going and going until finally they get heavy enough they just fall out. All right, so that takes place in the cloud with a lot of different sizes of water droplets. They bump into each other, they merge, and they fall out of the sky. Cold clouds, which is obviously what we get this time of year. In the winter, you've got a mixture of ice crystals, which are snowflakes, and that supercooled water droplets. Microscopic, very tiny water droplets, but liquid. So you start by having a mixture of those two. But because ice crystals, all right, that's a solid, it's a lower energy state than a liquid, all right? But I've got a liquid that is below the freezing point. So I got liquid in a cloud that's below a freezing point. So if you want, it wants to freeze, but it's got to find something to freeze on, but it's really eager to freeze on something. So if I got a snowflake here and a liquid water droplet here, and I'm in a cloud that's 15 degrees Fahrenheit, all right? If these things get close enough, my liquid water droplet is basically going to deposit itself onto that snowflake. So in this cold cloud precipitation process, my snowflakes, the number of snowflakes, are growing at the expense of the liquid water droplets. Right? My cloud is below the freezing point, below 32 Fahrenheit, but I got super cool liquid and I got ice crystals here. And these stuff start to get close. My snowflakes are going to grow at the expense of those super cool water droplets. Snow is the same. Snow is just a special type of ice crystal. So if I say snow, I say ice crystal, I mean the same thing. There are different shapes of ice crystals than all the pretty dendrites like we like to draw since we were 6 years old. There's lots of different shapes, but the point being is that ice crystals will grow at the expense of these super cool water droplets. And then if the temperature down here, the ground is above freezing, the snow melts and we get rain. But if the entire depth of the atmosphere is below freezing, then sure enough, we get snow all the way to the ground. So rain is basically liquid water drops, and the raindrops are generally they're generally about half a millimeter, all right? And it comes from those nimbostratus clouds, like I said before, or the cumulonimbus, the thunderhead clouds, all right? So rain is rain. Drizzle is liquid, but the droplet size is smaller. Drizzle, sometimes that term gets tossed around. Drizzle always says very light rain. In the vernacular, in the lexicon, okay, that's fine. But when we're looking at climate, when we're looking at weather, we talk about drizzle, we mean water droplets that are water drops, precipitation that is smaller than raindrops, half as small as a regular raindrop. And these, so they don't fall as fast. This is what we think of as mist sometimes. All right. And this will eat you up when it becomes frozen drizzle, which I'll get to in a minute, because it's liquid until it touches something and then freezes. But again, drizzle, it's tiny, tiny liquid. It's just kind of hovering in the air. It does fall very slowly, but not nearly as fast as legit rain is falling out of the sky, because the pieces of liquid just aren't as big. And that drizzle generally forms lower in a cloud than rain does. Legit raindrops do. Snow is just, I love this, agglomeration of ice crystals in the form of flakes. There are different types of ice crystals. There's dendrites, there's plates, there's columns. There's all different shapes of ice crystals. And that depends on precisely what the supersaturation is of the cloud. In other words, how much moisture is in that cloud and what the temperature is of that cloud. That goes a long way in determining what the shape of your ice crystal is going to be like. All right. Ice pellets, also known as sleet, is basically I got snow, all my precipitation starting to snow in the winter. It starts to fall. It melts on the way to the ground into liquid. And then in the last few thousand feet of the atmosphere, it freezes again because I've got a very stable atmosphere. So down here close to the ground, it's below freezing. So I have a liquid that's coming through a very cold layer of the atmosphere below freezing. So that liquid just freezes into ice. It doesn't go back to pretty snowflakes. It just is a little round ball of ice. And that's ice pellets or sleet. Freezing rain or freezing drizzle, and that's a liquid until it touches something and then freezes. That's what coats power lines and trees and forces them to hang all over themselves. All right, so freezing rain is liquid until it touches something and then it freezes. That's what really messes up the roads. That's what messes up the power lines. That's what snaps trees. Sleet doesn't snap trees. Sleet bounces, and you could scrape that away if you're on it fast enough. You cannot scrape freezing rain. That's a glaze on stuff. That is big time trouble. Hail is it's a round ball of ice, has the same shape as sleet, but hail tends to be bigger than sleet, and it forms in a different way in a cloud. Sleet is one way, down. Hail forms in thunderstorms. And because thunderstorm clouds are very, very deep, 20, 25, 30,000 feet deep, 6 miles, and has multiple temperature layers because it's summer, so the ground is 70 degrees. The freezing level in these clouds, 15, sometimes 20,000 feet. You can have precipitation forming and it starts to fall, but you have these massive updrafts, this air rushing into the cloud, forcing air upward inside the cloud. Some of that falling rain gets caught up in those updrafts, goes back higher into the cloud and freezes again. And it becomes heavy enough to fall. Then there's another updraft that forces it up. back over the freezing level and it freezes again. So you start having these layers forming in hail. And you grow the really big hail out in the plains because they have because they have flatter land, they have thunderstorms that tend to have more laminar flow. The mountains aren't in the way of making thunderstorms. The ground is flat, so you have very well-defined textbook kind of thunderstorms. There's less friction than in the mountains and in the plain in the coastal plain here in the eastern U.S. Right, but hail is a summertime phenomenon. Right, that's jagged, sometimes circular pieces of ice that are falling down out of a convective cloud. Right. Finally, remote sensing of precipitation. Remember, remote sensing, you're not in something measuring it. You're measuring remotely. Doesn't necessarily have to be in orbit, right? Remote sensing of precipitation, the one that you know the best is just radar. There are satellite sensors of precipitation, but radars here on the ground, your radar is sitting on a tower that's, I don't know, about 100 feet above the ground, 150 feet above the ground, and it just sends out a beam in all directions. It's a little microwave beam. And of course, microwaves, it's the speed of light, so you can do this pretty fast. Sends out a beam, sees what bounces back, boom, turns, sends out a beam, sees what bounces back, boom, turns, sends out a beam, sees what bounces back. These are microwave beams, and they're very, very low intensity microwave beams by the time they get out 70, 80 miles. All right, so you don't have to have a very high reflectivity. You just need to have a reflectivity. All right, so how much stuff is out there, how strong your reflection is, your reflectivity will tell you how much precipitation is out there. That's the fundamentals of radar. You send out a microwave beam and see what bounces back. If it bounces back a lot, you got a lot of stuff out there. Now, to be fair, the radar itself doesn't say this is rain. I mean, there are aircraft radars that are looking for aircraft. There are other radars that are looking for airplanes, but that's why we're looking in the microwave part of the spectrum, specifically tuned to look for what they like to call hydrometeors, raindrops, snowflakes, hail, that kind of stuff. So that's the fundamentals of radar. You send out a microwave pulse, wait for it to come back, and see what it bounces off of. So that's the short version. Those are the real highlights. The full lecture notes are already online. I've got this recorded. I'll get this up online either later tonight or probably tomorrow, along with the next assignment. And that's when we'll talk more about the global atmospheric circulation, things like Hadley cells. What are the doldrums? What are the trade winds? What is all that? What's the polar vortex? We'll talk about all that next time. So that's it for tonight. Any questions before you guys go?
Is our exam next week?
Nope.
Or is it's the next?
Yeah, it's not next week. It's a couple of weeks away.
Okay. All right. I just wanted to make sure.
Now, I will give everybody at least a week's notice for that's coming.
Sweet. All right. Sounds good.
All right, everybody.
Thank you.
Have a good night.